Hello guys, hope you are fine. Just a quick explanation for assessment 3, the portfolio. So in the portfolio we have a parking shed frame, which is consisting of a frame with hinged support or bent support here. And this is a cantilever. So this is our beam. And this is our column. This is a tie or link member. The forces given are vertical loads G 2 kilonewton per meter, Q 1 kilonewton per meter, W ultimate or wind load 6 kilonewton per meter. And here we have G equal to 1 kilonewton point load, Q equal to 3 kilonewton as point load. From wind on the side of the column, lateral force, we have WU of 2 kilonewton per meter. The dimension are 3 meter, 4 meter. The height is 2 meter and 4 meter. The first step is to find the load combination. So for vertical loads, we have UDL and point load. For the UDL, the load combination, the critical load combination will be E D ultimate. This for ultimate limit state is G 1.2 G plus 1, plus psi c q plus W ultimate. In this case, psi c equal to 0, so it will be 1.2 G, which is 2 plus 6 kilonewton. So the uniform load will be 7.2 kilonewton per meter. For point load, the ultimate will be 1.2 G plus 1.5 Q, so it is 5.7 kilonewton. For horizontal load, we have only W ultimate equal to 2 kilonewton per meter. So this means that the forces we have on this frame are 7.2 kilonewton meter, and here we have 5.7 kilonewton, and here we have on the column 2 kilonewton per meter. So this is the first step, the loads or finding the load. The next step is to find the reactions. For the reactions, how many reactions we have? We have XA, if this point A, we have XA, YA, and we have a tension force in this tie, which is T. Okay, so we can remove this part. So we have only the force T. Okay, this force should be analyzed to two components, one vertical component and one horizontal component using the angle theta. So theta is in this triangle. So this 3 meter, 4 meter. So this is 5 meter. So sine theta equal to 0.8. Cosine theta is equal to 0.6. So the nearest component will be nearest to the angle theta. So it will be t cosine theta. And the vertical component will be t sine theta. Okay, so this is the first step. Second step is you need to also concentrate the uniform load here. So it is 7.2 times 4, so it is 28.8 kilonewton acting in the middle here. So 2 meter, 2 meter. Okay. Also, we have the uniform load here. So we need to concentrate this two uniform load. 2 by 4, so it is 8 kilonewton. 2 by 2, 4 kilonewton. So these are the forces we have. So we need to find the reactions. So for the reaction, we need to find if we take the moment at A equal to 0 here. So we have t cosine theta times the distance, which is 4 meter, minus 8 times 2 meter, minus 4 times 5 meter, minus 28.8 times 2 meter, minus 5.7 times 4 meter, all equal to 0. So from this calculation, T will be 48.5 kilonewton. So the force in the link member or on the tie, 45 kilonewton, and the sign positive, so it means it is tension as we assumed. So now we can replace this value with 48.5 times 0.6 and this 48.5 times 0.8. So if we apply summation x equal to 0, summation x forces equal to 0, so we have xa plus 8 plus 4 minus 48.5 times 0.6 should be equal to 0. From here, xa will be 17.1 kilonewton. Positive means the direction we assumed is correct. So this xa is 17.1 kilonewton. The next is y, summation y equal to 0. So if we apply summation y equal to 0, so what forces we have in y? We have ya minus this force, 48.5 times 0.8, and this force minus 28.8 minus this force 5.7 kilonewton equal to 0. From here we have ya equal to 73.3 kilonewton. So these are the reaction and the forces we need to find. And the next will be how to draw the straining action, bending moment diagram, shear force diagram, and normal force diagram. So we have here 5.7 kilonewton. We have the uniform load 7.2 kilonewton per meter. And we have here 2 kilonewton per meter. And we have distributed this load as 28.8 kilonewton. This one here as 4 kilonewton, 8 kilonewton. We have replaced this tie with these two forces. This one is 48.5 times 0.6. This one 48.5 times 0.8. The forces in this member is 48.5. We have found the reaction is, the two reaction is 17.1 kilonewton and 73.3 kilonewton. So for the normal force diagram, or the axial force diagram in FD, if we apply the normal force diagram, or want to draw the normal force diagram, so the normal force diagram on this tie is 48.5 kilonewton tension, and for this section here, what is causing normal force here? Normal force mean force perpendicular on the section. So if this is our section, so the force is, the vertical force is causing normal force. So the normal force at this section is 73.3. Then the next section or the next cut is here. So this is cut number 1, cut number 2. So at cut number 2, what we have applied, so 48.5 times 0.8. So we have 73.3 minus 48.5 times 0.8, which give us, so we will stay constant and then reduce 48.5 times the 0.8, so we reach 44.5. Okay, so just make sure the numbers are okay. So 73.3 minus 48.5 times 0.8, so we reach 43.5. So then we go straight until the edge here. So if we look at this cross section, this cut from top, so we have 5.7 plus 28.8, so it is 43.5. So all this is compression. Here for this two cuts, number 4 and number 5, we don't have any force perpendicular to this cut, so the normal force here is 0. So we have normal force on the column. The maximum normal force is 73.3. Okay, so this for the normal. For the shear, or for the moment first, start with the moment. Bending moment diagram. So for the moment on the thigh equal to 0 because there is no moment on thighs. And we have here cut 1, cut 2, cut 3, cut 4, cut 5, cut 6. So the moment at cut 6 is 0 because we don't have any moment at section 6 here or 5. The moment at section 4, so I can write it here, M4 will be, if we look at M4, so we take this part. So at M4, this force and this force are causing moment at section 4. So M4 will be 28.8 times 2 plus 5.7 times 4. So the moment is 80.4 kilonewton meter. So this is the moment. And because the two forces in this direction, so the moment will be at the top here because it is cantilever, so the moment should be above the datum. So the moment here is 80.4 kilonewton meter, and because we have a uniform load, so we have a parabola. So this is the moment here on the cantilever. The moment at section 4 and 5 here should be same. So M4 equal to M5 because at this two section it should be equilibrium. So if this moment M, so this moment is M. So the moment here will be 80.4 kilonewton meter. Okay, so we still need to find for section 3, 2, and 1. If we look at section 1 here, so for section 1, it is better to study this part from bottom. Okay, so for this one, there is no moment at section 1 because it is the start of the building or the structure. So we have the moment here is equal to 0. At section 2 here, so we study this part. So what causing moment at section 2? M2 will be the reaction, this reaction, 17.1 times the distance 4, because we are here. So the distance from here to here 4, plus 8 times 2, because this force in this direction and this force also in this direction. So both of them in the same direction. That's why we add them together. So the moment here will be 84.4 kilonewton meter. So the moment at section 2 is 84.4 kilonewton meter. From 1 to 2, from here to here, we have the uniform load. So we need to connect them with a parabola. Then from section 3 to 4, we connect it with a parabola. So this is our moment. The moment is negative on the column and the moment is negative on the cantilever or on the rafter itself. The next is drawing the shear force diagram. This is the shear force diagram. So similar to bending moment diagram, there is no shear on the cantilever, and we have cut 1, 2, 3, 4, 5, and 6. So we have 6 sections for drawing the shear. So here at section 1, what causes shear at 1 is the reaction, the horizontal reaction that causes shear at 1. So we have 17.1 kilonewton. Then from 1 to 2, we have the uniform load 8. So for the uniform load, we subtract 8, so we will reach 25.1 kilonewton, which is V2 equal to 17.1 negative 17.1 negative 8, so it becomes negative 25.1 kilonewton. Then at section 3 here, we have this force 48.5 times 0.6, which is equal to 29.1. So from 25.1, we go to the left with 29.1. So V3 will be negative 25.1 plus 29.1 give us 4 kilonewton positive. So on the other side, 4 kilonewton. Then from 3 to 4, we have the force 4 causing shear. So from 4 minus 4, it reach 0. So V4 will be plus 4 minus 4 equal to 0. So this is positive shear, this is negative shear. For the horizontal part, we have the shear will be the parallel force to the section. here. So we have, what is the parallel force from this part? We have 73.3 minus 48.5 times 0.8. So we have V5 equal to 73.3 minus 48.5 times zero point 0.8 equal to 34.5 kilonewton. So the shear here, we have 43.5 kilonewton. Then V6 will be 34.5 minus 28.8, which is the uniform load here. So from 4 or from section 5 to section 6, we have 28.8 negative. So this will reach 55.7. So the shear here will go to up to 5.7 kilonewton. So this is how to draw the normal force diagram, shear force diagram, and bending moment diagram for the column and rafter of this shed or this frame. So when you design of rafter for strengths, the rafter will be designed on M star. What is the maximum moment on the rafter? It is 80.4 kilonewton meter. So this is how to design the rafter. Design of column for strengths. The column is subjected to maximum moment of 84.4 and maximum normal of 73.3. So for the column, we have M star and N star. N star equal to 73.3 kilonewton compression, and M star is 84.4 kilonewton meter. So you can use AS 400, 4100 procedure to find the design or the cross-section design of the rafter and the column. Okay. And for if you are designing the tie for strength, so the tie is under tension force equal to 48.5 kilonewton. So this is the three members need to be designed. The next is how to do that on the space gas model. So I will stop sharing here. Then I'll open the space gas. Okay, so I am now sharing my space gas screen. So if we look at space gas, so this is the software interface. So firstly, we need to draw the frame. So from structure, you can draw with nodes or members. So I will start drawing with members from the origin. So the first member is the column, which is 4 meter high. The first part is 4 meter. Then second part is 2 meter. Okay. Then we have 4 meter. Then to draw the height, we have 35.35. Then I connect the member here, so I can draw the beached roof. Then I will delete this part and this part. The other option is you can just draw with coordinates rather than the member. It's up to you. Then Here we need a node to connect to the tie. So nodes, we have to draw a node. The node would be -3 and 0y. So this is the node. So we need then to draw a member between this one and this one to create the tie. So this is the frame. The next is to assign the node restraint or the supports. So here we have hinged support and hinged support here. Okay, so this need to be hinge, apply, and you can show the support restraint from here. So this is hinge. Here also we have hinge. So from properties hinge, apply. Then we select to create the link member. We need to select this member, and from also properties, we need to like make the end release the end restraint for this member to make it a tie. If you want to show the end release, you need to click this option, which is the end release. So now we have like the tie member here. We have this member as a column. We have this member as a rafter. So the next step is to add the loads. So we can select this member here from loads. We have member distributed forces. So you can add load case one if you will do it one by one. So we have selected this member. Okay. So we select this member, load, member distributed force, load case one. Okay. I think it show in different screen. So loads, member distributed force. And you can enter the force. The problem is it doesn't open in this screen. Don't know why. Okay, anyway, so you can add the loads and then just stop sharing. Okay, so this is another like version of it. I have solved it earlier. So I have put the loads. We have the uniform load on the column, the uniform load on the rafter, and the 5.7 kilonewton. The next step after you add the load, you need to assign the material. So you can assume the steel as a material. So from material and under the library here, you select steel. So the member becomes steel. All the members should be steel. For simplicity, you can just assume all members with the same section because we just doing analysis, so it doesn't matter what is the section selection for all of them. So one option is to make all of them same section like that. So select all of them, and they already all has same section property. So if you select one similar to all, so you can select at a middle one in the table like 310 UB, then okay, then okay here. So this means that the section now is assigned to be all 300 UB. So this is our frame. Another option is you can change the selection of this member. So from the table, for example, if you want to make this tie as like, for example, a square hollow section or whatever the section you will be using, like whatever it is, like here. So click OK. So now we select a different section for this one. Sorry, just a second here. So probabilities, you need to change the number, otherwise all of them will be same again. So choose a different, give it a different number. So you can take it as SHS, or for example, 75 by 4, and then okay. So now you have a different member for the tie. If you want to have a different member for the beam and column, so you can select the column and make it another number 3 and choose a different section, for example, universal column, also one section in the middle here, and okay. So you have now member for column, member for beam, and member for the tie. And this is the applied load on them. So in the report, you need to show some screenshots like this one for the loading, for example, and then you will run the analysis, analyze the problem, all good with the problem. So this is the analysis. Then you can show the bending moment. So this is our bending moment, very close to what we got. And here is the shear, also quite similar to what we got. Just this diagram should be same values, but should be up above the datum. Here is the normal force. So we have here 48.5, 73 point 3, almost same. And if you want to show the deformed shape, but the deformed shape, you will need to create different load combination for the serviceability. So you need to have load combination for ultimate and load combination for serviceability. So what is, for example, if it is the load combination for serviceability, what is the maximum deflection for the beam? 57.88 meter. For example, if this exceeds the allowed allowed limit, so what you need to do, you need to select the beam again and choose a bigger section. For example, if 310 is not is give high deflection, so you can use 530, for example, and change the member to a bigger size. Then you need to run the analysis again, or run the model again. Then if we look at the deflection now, so the deflection now has been reduced to 43. This means it is reduced when you use bigger section size, so you can try and error until you satisfy the condition of the serviceability. Okay, I think that's it for the software. You just need to show this bending moment as screenshot, this shear force diagram as screenshot, this normal force diagram as screenshot, with the deflection as screenshot, to compare with what we have done in the manual calculation. So your report will include this calculation for loading and bending moment diagram, shear force diagram, and so on, and attach to it or combine with it the software results from here, moment and bending moment and deflection and so on. It's better to show one by one, because if you add all the drawing together, it will not be understood. Okay? I hope you understand the requirement of the portfolio, and please let me know if you need any help, any other assistance. Thank you, guys.